a multisection. Yeah, and so this actually makes it quite nice, this construction. Yeah? All you just need is, you need a few conditions on a triangulation that you can actually check on the triangulation. Yeah? So you want to find a partition of the vertices with certain properties. I mean, there's some additional properties that you need. You don't just need to have a partition into sets so that the partition sets give you connected graphs on one skeleton. There's a little bit more that you need. So we just draw part of what we want, just to remind you what we did. So in dimension 3, so what we did with the tetrahedra is we wanted to find a partition with a property that, if you look at the 4 vertices of a tetrahedron, then always a pair is in one of the partition sets, and the corresponding graphs spanned by these things in the one skeleton were connected. Yeah? And so then we said, well, this really pulls back nicely here from the one simplex. Yeah? Because the standard cubulation of the one simplex in this case had just the, so the cubes are really just defined by the barycenter. Let me make the barycenter yellow. Yeah, and so this is one of the cubes. It's a 0 cube, here's a 1 cube, and here's a 1 cube. Yeah, so these were our 3 cubes. And the way they meet these tetrahedra, and here, this, in this case really, this guy here pulls back to this 2 cube, and this guy here pulls back to this prism here. Yeah? So we have this guy here. Okay. And then whatever this cube here pulls back to is actually a regular neighborhood of this graph. Yeah? A regular neighborhood of the graph in the manifold, and hence the handlebody. Yeah? This here pulls back to the other handlebody, and the intersection is this closed surface. Yeah? So that's how we arrange things here. N equal 4. So there we had the pesky issue that some will have 5 vertices, not 4. So we sort of needed to divide up our partition sets. What I mean, so like this. So that every tetrahedron sort of has one of these singular vertices, these singletons, and the other ones it meets in pairs. Yeah? So this was this construction here. Again, I mean, this gives us this map here to the k-simplex. Okay, and then we said, well, the dual cubical structure here is determined by the spine here inside. So this is now not a spine in the sense that I defined here, yeah, because it meets the boundary, yeah. Okay, and again we said, well, so these things here we arrange for everything so that the preimages of vertices are connected graphs. Yeah, so that's what we got. Preimages of vertices were connected graphs, and so their neighborhoods are the handlebodies. And then if you look at the double intersections of handlebodies, they're really the preimages of these cubes here, the dual one cubes, yeah. And then we said, well, okay, so if you think about this dual 1 cube, here you can collapse it to just the barycenter of the edge, and this collapse actually sort of pulls back to a collapse here from the intersection to the preimage of this barycenter of an edge. And then we said, well, okay, so these guys here, if you look at this picture here, I mean, this barycenter here just pulls back to 1 cube. We're happy with this, but this barycenter here, for instance, I think I've run out of colors, so let me make this here blue. Yeah? This barycenter here folds back to actually a 2 cube. And we didn't like this so much, yeah, because we wanted the spine to be one-dimensional. And then we need to look at this in detail, right? We need to look at actually the link, yeah? The link of this guy here, a face, and we saw that in the specific construction that we had, this quadrilateral here actually had a free side that you could collapse further, yeah? So it had a free side, you could collapse it further, and so you got something one-dimensional, yeah? So that was the specific construction we had there. Okay, but so this was something that created some work. Okay, and then if you go to n equal to 5, why not? Let's be brave, right? Just a matter of drawing 6 dots. So I have a picture like this here. So you see here, you can again do something a lot more symmetric, yeah? Because here you can just pair the vertices up in a simplex, and again, instead of maybe think of one scatter, I don't know whether anyone knows a better way of drawing a 5 simplex. So anyway, here it is, yeah. And so so again, you just define this map to this guy here. Like so. And in this case, you will see that it's actually automatic, yeah? That these spines have the right dimensions, the ones that we sort of wanted. So let's look at this here. Right? If you think about the 5 simplex, I mean so again actually the triangulation to do here, so in odd dimensions, just take K to be L prime, where L is any triangulation. Yeah, just take the first barycentric subdivision and then do what we said in our labeling scheme. Yeah, so these here would be the, say, barycenters of 0 and 1 simplices. These are barycenters of 2 and 3 simplices. These are barycenters of 4 and 5 simplices. Yeah, just as you did it here, barycenters of 0, 1, and 2 and 3 simplices. Yeah. And then again, you get the connectedness for free, and the other property that you want is really just these kind of codimensions. Yeah, but here, then, if you look at the, say, I mean, any handlebody, of course, has a one-dimensional spine because it's pulls back to a neighborhood of the spine. If you think about the double intersection of 2 handlebodies, and also complete symmetrical picture, it's enough to look at one. Again, you say, well, this is actually the pullback of this dual cube here. The collapse here lifts to a collapse here. So all you just worry about is what is the preimage of this guy here. Yeah? And the preimage of this guy here is just going to be a quadrilateral in this tetrahedron. Yeah? So it has dimension 2, and this is exactly what you want. Yeah? So here you get something 2-dimensional just for free. Yeah? And that's how it happens in each odd dimension. You basically just get these dimensions for free from the way you've constructed the map. Yeah? Okay. And so then the only work is really to adjust things in 4 dimensions. And the main issue here was to sort of not have isolated vertices, but make everything into a connected graph. And then also show that in the end, you get this kind of collapse of dimension here. Yeah? So that's the sort of harder part in these dimensions. Okay. Yeah. So maybe that's all I want to say maybe about the proof, unless you want to know something else. Let's sweeping maybe some of the details under the rug, but most of them are quite, well, at least intuitively convincing. Yeah. Okay. So this is how you get these kind of multisections. Yeah. You really can think of this as map to a simplex and then pull back whatever you have. Okay. So let's maybe just because I've only drawn 1 and 2 things, let me draw the dual skeleton in the 3 simplex as well. So in the 3 simplex, which would be the next guy, right? I mean, it's exactly this thing here. Yeah? It's this kind of butterfly that's sitting inside that leaf. Okay. Yeah, and so here again the cubical structure is, I mean, for each vertex you have this cube here, the space at the vertex. The double intersection of two handlebodies, say the one at this vertex and the one at the top vertex, is this cube here, which is this 2 cube. And again you see that this 2 cube, of course, you can collapse, yeah? You can collapse sort of first to the boundary maybe of the simplex to these 2 arcs, and then you can also collapse it further, yeah, from the arcs into just the barycenter of the one simplex. Yeah? So that's really just the key observation here, that these collapses here, by the way you define these maps, I mean this is simply a map, you can just lift them to your manifold. Okay. And then if you think about the triple intersection, so take 3 of these guys, so maybe this guy, and this guy, then the triple intersection corresponds to this one, and again you can sort of pull it back. Yeah? And the quadruple intersection is then just the barycenter here. Yeah? Okay. So, but that's the sort of the main thing that's going on there. Okay.
So at the end you only have to worry about the pieces of the barycentric division which are on the boundary of the simplex. This collapse.
Yeah, exactly. Yeah. Mm-hmm. Yeah. Okay. So then, so this multi-sections in arbitrary dimensions. So let me just say something briefly about sort of what we call the recursive structure, and also say something about non-positively curved cubings. So what you see here is, if you look, say, at a say this 5 manifold, and this 5 manifold has a nice trisection. Yeah? So the 5 manifold has a trisection. So this is now here 5 manifold. And then if you think about the boundary, if you think about the boundary of one of these trisection, so one of these trisection manifolds, yeah. So then this now has a very nice sort of decomposition. I mean, it has so this is something now that is decomposed into 2 3 manifolds. Yeah. So here you see this 1 3 manifold. Here you see this other 3 manifold. Yeah. But they don't necessarily have spines of dimension 1, but just of low codimension. Yeah. And so this is sort of how you see that actually so a multisection of a manifold induces then also multisections on sort of but these are sort of generalized multisections, yeah, on the regions, yeah, in the boundaries of these handlebodies, yeah, and this propagates then through the dimensions, yeah, and I don't know what this might be useful for. It might be useful for some inductive arguments or something if one ever gets to that stage where one needs it. Okay, so let's maybe just move on to the non-positively cubing. So here's a theorem. So every P manifold has a triangulation supporting the multisection. What I mean with this is really just that, yeah, the triangulation uses a simplicial map and the pullback is multisection such that the central submanifold has a non-positively curved cubing. Okay. So I should ask, so he's familiar with cube complexes and non-positively curved cube complexes. Okay, well, he's not familiar with them. Okay. Yeah, so I should say something. So cube complex is really just something that's made up out of standard Euclidean cubes. So let's call them 0, 1 to the m, just standard cubes. And you identify them using isometries along facets, or faces. So let's just draw sort of an example. I mean, here's sort of a cube, and then what you can do is maybe here you can sort of stick on. So here I've taken a 3 cube. You can stick in a 2 cube. You can also, if you wish, stick in a 1 cube, and do basically things like this. So there's no one stopping you from doing anything. Okay. And of course a nice sort of thing also to think about is just surfaces made up out of quadrilaterals. So here's maybe one example of a disk in this case. A disk made up out of 3 quadrilaterals. Okay. And then if you look at the link of a vertex in this, the link of a vertex in such a cube complex, so if you pick your vertex, the link is going to be a simplicial complex. So here's the link of this vertex. So if this is V, and this is the link of V. Let's maybe pick someone more interesting here. So here's my vertex V, and then here the link is going to be, well, sort of, I get a triangle here, a 2 simplex from this guy, and I get a 1 simplex from this guy. And also, I mean, no one's stopping you from doing something like this here. So if you think about this guy here, then the link is going to be this thing and this thing here. So no one's actually saying that it will be connected. Okay. So these are some vertices and their link. So the link of a vertex is a simplicial. Okay. And now then, a simplicial complex is so there's a very useful notion here. It's a flag complex. If whenever you see the 1 skeleton of a k-simplex, you have a k-simplex. Or I guess another way, I never understood this way of putting it, is that every non-simplex contains a non-edge. If that makes any sense. Complex is flag if each subgraph in the 1 skeleton isomorphic with the 1 skeleton of the k-simplex is in fact 1 skeleton. So just to give an example, so if you look at this guy here, and the link of this vertex just consists of these 3 1 simplices, But these 3 1 simplices, I mean, they are isomorphic to the 1 skeleton of a 2 simplex, but there is no 2 simplex, So this thing here, this link here is not flag. well, here, I guess this here is fine, right? This here is filled in, yeah? And so here you do have this triangle. Okay. So in particular, I mean, if ever you see, right? If ever you see, so something like this here, then there should be a 3 cube, yeah? There should be a 3 cube in this cube complex, yeah, that has this triangle in as its boundary. Okay. And so why is flag good? So flag actually, so it's an observation by Gromov, that this flag condition actually gives you some geometry. Yeah? So here's the Gromov-Lind condition. So the Gromov-Lind condition says that the cube complex C is negatively if the link of each vertex is flag. Okay. And so what does negatively curved mean? So C negatively curved. So one way of saying it is that the so cover, yeah, is cat 0. That's it. And so in particular, I mean, the cover is contractible. Should I say something about cat 0? No one's nodding. Okay, so I will not. Yeah. So with just this very simple, and so the main things that you really need for a flag complex. I mean, so basic facts. So the first thing is that barycentric subdivision of any complex is flag. And the second thing is that the link, so now the link in the sense of simplicial complexes of any simplex in a flag complex is flag. Okay. So that's I think all I need. That's all I need to give you wishy-washy proof of non-positively curved cubings. So let's sketch the proof of this theorem. Yeah. So let's think about the odd dimensions first. So n to k plus 1. Yeah. And just to maybe, yeah.
I failed to see the first basic fact. Can you draw it on the barycentric subdivision?
Yeah. So the first, right? Mm-hmm.
Any complexity line?
Yeah. I guess maybe it helps to just draw a simplex. Yeah. The two simplex. And then, sorry? Yeah, okay, but it's really just that makes it sufficiently fine, yeah, that you will be flagged. Yeah. Mm-hmm. Yeah. Okay. Okay. So just as in the existence proof, so we start with any triangulation and we take the first barycentric subdivision, and it gives us our map then to the simplex. So let's maybe draw the picture in dimension 5 with something to go by. Here's my simplex, and it maps to this guy here. Yeah? And so now I'm thinking about the central submanifold. So central submanifold is the pullback here of the barycenter here. Okay. And so what I want is, so I know, here we know, I mean here we have our map 5 from M to the k-simplex. Yeah? And we already know that phi inverse of the barycenter, so let's call this here little b, yeah, is cubed manifold. Okay. And so what we want to need, what we need to do is we just need to check the link condition. Yeah? We need to check Grommer's link condition. Okay. And so I need to check the link condition at every corner basically of this cubed manifold. So what does the corner look like? Well, it sort of sits on one of these faces that has 3 vertices or 3 distinct colors. Yeah? So here's sort of my corner C of such a cube. Okay? So here's a corner of a cube. And now I need to worry about sort of what does the link of this little corner look like. Yeah? So the first thing I could think about is then the vertices. Yeah? So vertices in the link. Yeah? And maybe if I draw sort of this as okay, let's. I mean here I'm in dimension 5, so really I mean this is a corner of 3 cube. Yeah? So here's my corner C, and I want to explore really the link, yeah? The link of this guy here. Okay. So the first thing to worry about is, well, what are the vertices, right? And how do I see the vertices? Well, the vertices correspond really to edges of the cube, yeah? And the edges of the cube correspond to what? I mean here, if I think about this guy here, the edges of the cube inside this triangle really correspond to, so if I take one of these vertices, the red vertex, and I connect it up to this red vertex here, right? That actually gives me an edge in the cube, yeah, because it gives me this tetrahedron with these colors here, and it gives me this edge of the cube sort of going to the center, yeah, the barycenter of this triangle here. Yeah? So this is this edge. This is one edge in this cube. Yeah. So this takes me from C maybe to C prime. Yeah. Yeah. So this is exactly what they correspond to. So this means that the vertices, yeah, in the link of the cube really correspond to, in this case, then actually the vertices in the link, yeah, of this guy here. Yeah? So the vertices in the link of this 2 simplex correspond to the vertices here. And that of course sort of propagates throughout the whole triangulation. Yeah? So you see that you get a bijection between the vertices of the link in the sense of the simplicial structure here in K prime of this 2 simplex. So let's call this here delta K sub C. Yeah? So in general it's a K simplex. Yeah? You get a bijection between these and the vertices of the link in the central submanifold, and here the link now thought of in the sense of cube complexes of this corner C. Yeah? So you get this kind of bijection, and this actually now goes to all higher dimensions, right? And if you think about the sort of an edge here, what does an edge correspond to? Well, in this case, then it doesn't correspond to a vertex; it corresponds to an edge here. Yeah. And if you think about this two-phase, what does a two-phase correspond to? Well, actually, it corresponds to this two-phase here. Yeah. Okay. And so that's how it carries on in the whole triangulation. So you actually get a simplicial isomorphism from the link K prime delta C to the link in the cube complex of C. Yeah? Okay. And I mean, how do you know that you get everything this way? Well, the thing is, here I'm talking about a piecewise linear manifold, yeah, and then the PL triangulation of this, yeah. So the link of this here will be a standard PL sphere. Yeah? So that really tells you that there isn't sort of some some random and odd stuff hanging out somewhere else. Okay. So this is how you basically check the Gromov link condition in odd dimensions. Okay, and then in even dimensions, let me just sweep this completely under the carpet. So what did we do in even dimensions, right? In even dimensions we said, well, you have these kind of singletons in our construction. You have a singleton here, you have a singleton here. You sort of have these things here, these things here. So here's this three-phase connecting two of these pentachora, which is another name for a four-simplex. Yeah, and then we said, well, what we do is we just do these kind of 2-4 bistellar moves. Yeah, so we did this 2-4 move, but the problem is, or in higher dimensions, is then a 2K move in that case. Yeah, but the problem is in dimension 6 and higher, this destroys the flag condition. Yeah, so when you do this, the complex you get after it is not flag anymore. So ouch. Yeah. So the thing is actually the trick, we found then a trick to arrange for the same thing, but not using the first pericentric subdivision, but using the second pericentric subdivision. Yeah. So it's a more complicated labeling scheme. I mean, it's in some sense again quite elementary, but it's more complicated, the labeling scheme, to basically make everything work. Yeah. In some sense, I mean, that's also something one could have done in the existence proof, but it just seems to just take away from the basic idea. Okay. So anyway, so this is sort of how you get these. This is in a nutshell how you get these non-positively curved cubings for the submanifolds. Okay. So maybe I said I was going to mention open problems in the end, so maybe this is sort of the first open problem, is sort of a realization. Problem. Which is a bit like a version of a Whitney embedding theorem, but for positively curved cube complexes. Yeah, so n a k-dimensional closed k-dimensional closed manifold with non-positively curved cubing. And then the question is n the central submanifold? In a multisection of some manifold of dimension. Well, so the dimension.
I want to come back. So Stephan continues the second talk.
Well, thank you. So, and I guess I had given an outline on Monday, so I just have to stick to it. So let's see. So I want to talk about what this tells us about finitely presented groups. Yeah? So if gamma is finitely presented group, result is that there is a closed four-manifold that has gamma as its fundamental group. Yeah, so then there is a closed four-manifold, so M with pi 1 of n isomorphic with gamma. Yeah? So I thought maybe I just give a quick proof of this fact. Just to have proved something at the beginning of the lecture. Yeah, so gamma has presentation, say with generators G1 up to Gn, related R1 up to Rm. Yeah. So now we want to build a manifold with fundamental group, really defined by this presentation. So the first thing to do is just build a closed four-manifold with fundamental group. So we just take the connect sum, say n, the connect sum of n copies, yeah, of S1 times S3. Has a fundamental group, a free group. It's closed four-manifold with pi 1 of n free group of rank n. And then, of course, in this four-manifold, we can now take loops. I mean, the generators, the relators are really words in the generators. So just take simple closed loops corresponding to these relators in N. Yeah? So in N can take simple closed curve gamma I corresponding to Ri. And if we drill this out, then the fundamental group does not change. Yeah? So now pi 1 of n is the same as pi 1 of n minus gamma I. And in fact, I mean, we can take out the whole collection. Yeah? So whole collection of these gamma i's, and when we drill out now a neighborhood, of course, we can take a tubular neighborhood. So drill out tubular neighborhood of gamma I. So this is really then of the form S1 times B3, and then we can basically kill gamma I by just sticking in S2 times B2. Yeah? So that's what we do. Then so the boundary of S1 times B3 is just S1 times S2, and glue in S2 times D2, yeah? And here note, of course, the boundary of S2 times D2 is the same as this here, S2 times S1. And this here has fundamental group, trivial group, and so by Seifert van Kampen, we get a manifold with fundamental group, what we wanted, yeah? So by Seifert van Kampen. Sorry, yeah, that's Seifert. The resulting manifold has pi 1 isomorphic to gamma. Okay. Yeah, and so this is where and this here is really, so this is the step where it fails for surfaces, right? And we cannot find a closed surface with free fundamental group. Yeah, so this is somewhere where it fails for surfaces. Of course, you could do this step with 3 manifold by just taking S1 times S2. And you can still find also these simple closed curves, that's fine. But of course, this thing here does not hold in the case of a 3 manifold, yeah, because the codimension is not greater equal to 3. Yeah? So this is where in dimensions 4 and above you can do this. Okay. And so now that we have this, we can of course trisect our 4 manifold. Then now trisect. Yeah, and so let's recall what this means. And it really means that I think of my 4 manifold as chopped up into 3 handlebodies, H0, H1, H2. And the pairwise intersections are always a 3-dimensional handlebody. So these are my H01, H12, H02, say. And then the triple intersection is a closed orientable surface. So here's sigma. Yeah? Okay. And actually, this trisection diagram gives me basically a push-out diagram for the fundamental group. So this gives me that pi1 of n is really the fundamental group of a graph of groups, where you put the surface group here, you have a surjection onto a free group, which is pi1 of H0. You have a surjection onto free group here, which is pi1 of H1, and you have a surjection here to pi1 of H2. Yeah. Okay. So this is a generalized graph of groups. Yeah, where I think of my edge groups as pi1 of the surface, and of course these things here are isomorphisms, the canonical isomorphisms going back here. But then these guys here are just surjections. Yeah, I mean, usually when we think about a graph of groups, all the maps are injections. Yeah, but for a generalized graph of groups, they just need to be homomorphisms. Yeah, and you have sort of a similar construction. So there's pi1 of a generalized graph of groups of this form. And so this means now that every finitely presented group you can actually think of as this way. You have a surface group, and you have 3 free groups, and you have these surjections. Yeah? So every finitely presented group now has this kind of decomposition. You can go even further and really draw in all the groups that are involved in this. Yeah, I mean, here we have 3 more groups. We have the groups here from these handlebodies, and of course a fundamental group of the surface surjects each of these 3 groups as well. Yeah, so you can go even further and sort of draw yourself a cube of groups. So let's do this. Not sure if I've chosen sort of the best perspective for this picture. Let's just wait and see. Yeah, maybe this is not the worst way of looking at it. So yeah, so I have this cube of groups where here I see pi1 of sigma, and then one thing that I see here are these kind of surjections onto the double intersections. So here I see this surjection, here I see this surjection, maybe this is H02. And then on the back, I have H12. And of course here, everywhere, I should write pi1, pi1. And then these 2 here, I mean, these are the handlebodies now in the boundary of H0. Yeah? And each of these actually suggests the fundamental group of H0. I have these surjections here as well. So this is pi1 of h0. Then this guy and this guy both go to pi1 of h2. And then this guy and this guy both go to pi1 of h1. And then each of these here surjects the fundamental group of the total manifold. Yeah? And so again, you can think of this now for any finitely presented group. You could say, well, here's my arbitrary finitely presented group, and I can actually realize it as this kind of cube of groups. So this is now not, this is now not the fundamental group, of this graph of groups. So I don't think of this as a graph of groups, because if I thought of this here as a graph of groups, this would always be have infinite group, would always be infinite. But I mean, here we're talking about all groups, so in particular you also get finite groups. Okay, so so you can always think of it this way. And another thing that you can notice is that actually if you do a stabilization, right, we said we can stabilize trisections by doing these kind of moves where, here's H2, here's H0, here's H1, I can increase the genus just of H2 by sort of adding another one handle that I drill out from the double intersection H0, H1. So this increases the genus of the surface. It stabilizes the Hilbert splittings on the boundaries of H0 and H1, and it increases the rank of this free group here. So there's a natural stabilization here that comes from topology, but you can of course also, in terms of the group theory, you can do a similar stabilization. So you have sort of a manifold stabilization. You see some kind of group stabilization. Okay. And so now to go back, so I learned this from David Gay. He told me about this in an email. So Abraham's, I need to know how to spell his name, sorry. Alan Abrams, David Gay from Kirby. They basically realized that actually there's a way to go back. You can go back from such a diagram of groups to a manifold. So they have a way of going from a group trisection to a manifold trisection. So this is more involved than what's happening here, right? Because you really need to think about all the ingredients. You actually need to start with the surface. So you have your surface group, and this means you start with the surface. Then you have these surjections onto the three-dimensional one-handle bodies, and you need to now then realize these as an inclusion of the surface into the boundary of a three-handle body, and then you need to realize these maps here as well, topologically. Okay, so this is basically using, one thing that you use is of course parallelism. Saying that the only sort of the first three manifolds with three fundamental group are really connect sums of S1 times S2, and then it uses also classical work of Laudenbach and Kröner. Okay. So this means you really get sort of this philosophy. That's maybe all it is. That's sort of a smooth or PL four-manifold topology is really the same as the theory of finitely presented groups. And that basically the stabilization moves. I mean, you can also talk then about so stable equivalence classes of groups, yeah? And in particular, this means that you could really, if you wanted to, yeah, formulate the four-dimensional smooth Poincare conjecture just as a problem in group theory, yeah? So this sort of, this may be something that might have made Stallings or someone happy, yeah? But yeah, it's of course a question how useful this is, yeah? So consequence is that the four-dimensional Poincare conjecture can really be formulated in terms of groups. So four-dimensional smooth Poincare conjecture can be formulated as problem. Yeah, so maybe this is more or less what I want to say about finally presented groups. Yeah, and of course you can sort of generalize these things also to higher dimensions. Yeah, in higher dimensions, of course, you have more handlebodies, so you get sort of diagrams where more and more groups are involved. Yeah, you can either sort of think about them this way, or you can think about them this way. Yeah. Okay. Good. So then maybe let me just say now what a multisection is of a higher dimensional manifold, because we've only seen one example so far, which was complex projector space, and there was really this way of visualizing it using the moment map and getting this decomposition into balls. But we haven't seen anything else here. Okay, so here's the definition. So M is a closed, connected PL manifold of dimension n, and then a multisection of M. It's a collection of k plus 1 submanifolds and I'll call them H0 to HK, where, so it depends whether n is even or odd, so n is either 2k or n is 2k plus 1. Yeah, so this matches what we've seen, right? I mean, for 3 manifolds, k would be 1, so you get 2 handlebodies, and for 4 manifolds, k would be 2, and then you get 3 handlebodies. Okay, such that, of course, the first condition is we want these guys to be handlebodies. Yeah, so each HI is standard n-dimensional one-handed body. And the second thing we want is, just as in our picture, we want the interiors to be pairwise disjoint. And the union, of course, we want to be the manifold, and it's the union of all of these HI. And so what's the next condition? So next condition is now we need to think about these intersections. Yeah, so we need to think about intersections of 2 or more of these handlebodies. Okay, so the third one is that if you take an intersection, so H, say A1 intersect HIR, where you take at least 2 and at most k, yeah, so not all of them, yeah, then this is a compact connected submanifold with boundary. Also, and when I say with boundary, I mean with non-empty boundary of and so now I want to the dimension is of course determined by the intersection that I've taken. Yeah, so dimension will be n minus r plus 1, and so now comes the condition, and somehow the idea is I want to generalize this picture here, right? Where so in for a 3 manifold f h0 and h1, these are just handlebodies meeting the surface. Here all of these guys are again meeting the surface, but then these things here are handlebodies, yeah? And it seems too much to ask for that each of these intersections here is always a handlebody until you get to the end. Yeah, so at least we couldn't see a way to make this work. So the right generalization just seems to be that you just ask for the spines to have low dimensions. Yeah, so that's the condition. And as a spine of dimension r. Yeah, so that's exactly how many you've intersected. But then, of course, in the case of 4 manifolds, that's not what we want, and we intersected 2. But here we actually get dimension 1. Yeah, and that's really what we want a trisection to be. And that happens actually in all even dimensions. So in all even dimensions, if you intersect k of the handlebodies, you can actually make the spine, the dimension of the spine, drop by 1. So, so that seems to be the right way to think about this. And that really comes from the fact that, I mean, I'll talk about this in a minute, that it really comes from the fact that you're mapping to a k-simplex. Yeah? So except if I equal k, and n equal 2k, and then the spine has dimension r minus 1. In which case the spine dimension r minus 1. Okay. And so these guys, just because I'll keep talking about them, so I call these here the multi-section manifolds. Yeah, or the multi-section sub-manifolds. Okay. And then last, of course, the intersection of all of them. This is a closed and connected submanifold. Whenever I say submanifold, I mean piecewise linear submanifold. And of the appropriate dimension, right? Of dimension n minus k. So this guy is called the central submanifold.
Where is k plus 1?
I beg your pardon?
Hk plus 1, where is k plus 1?
Oh, hk. Oh, sorry. Yeah. Very good. Okay. So then maybe to just clarify what I mean when I say spine, because there are different ways of thinking about spine. So here spine, so if M is compact with non-empty boundary, and P in the interior of M is a polyhedron, then this is a spine. And then if N collapses to P in the piecewise linear sense, yeah? So you can just collapse basically N, because I have non-empty boundary, you can start collapsing it from the boundary onto P, yeah? And the main thing here is that I want P to be contained in the interior of N and not meet the boundary. Yeah? Okay, so with this then, I mean the first guy, so the first condition is then pretty equivalent to saying that each HI has spine a graph, yeah? So each HI has spine a graph. Okay. Good. So now I wonder what's the best thing to do. Maybe one way to see what's maybe going on here and what one has is to think about sort of the dimension versus how many handlebodies one intersects. Yeah? So if I think about, say, dimensions, I'm going to start at dimension 3, 4, 5, 6. I don't know, how far do you want to go? Do you like 8 manifolds? Let's see, these are my things, right? So if I think about the R, the number of handlebodies, right, and this is an HI, this has dimension 3, here it has 4, here's 5, here's 6, here's 7, here's 8. And then next to it I could write the dimension of the spine, yeah? And the dimension of the spine here is always 1, yeah? So here I write dim N slash dim P, yeah? Where P is a spine. So this is what these numbers mean, yeah? And then so if I intersect 2 of these dudes, so that corresponds to HI intersect HJ, then of course the dimension just drops. And here I'm done, yeah, because I get my surface, and here I don't talk about spines anymore. Here you get something 3-dimensional, and this is where the drop of dimension happens. Yeah, so because this is now the half dimension, yeah, 2, so half dimension, so the spine stays of dimension 1. Whilst here it just drops by, well, it's exactly the number of handlebodies they intersect. Yeah, and so here it's 5. And 2, here's 6, and 2, here's 7, and 2. And then if I think about triple intersections, of course here I don't have them, here I get something of dimension 2, and I'm done, yeah? Here I get something of dimension 3, and the spine has dimension 5, I'm done, yeah? So here I'm done as well, right? Because here, of course, also I do trisections. Then here it's 4 and 3, and here it's 5 and 3, and here it's 6 and 3. Okay. And then we go on. So if we go now to intersecting 4 things, so 4 I don't have here and here, but here, so here I get something 3-dimensional, here I get something 4-dimensional, and the spine has dimension 4, and here I get something 5-dimensional, and the spine has dimension, I'm confused, 7, 6, 5, 4. Yeah, so this is, sorry, I mean here the even dimensions, yeah? And so I was confused about the 3 here, but of course here I'm in even dimensions. And so you see the drop in dimension again, yeah? So that's what's happening here in the even dimensions, that I get the additional drop in dimension. And so here, again, I go down to 3, yeah? Okay, that makes more sense. Pretty good. And then, and also here, where I've written 4, I mean, I'm done. That's the thing. This is the last intersection I can do, and I don't talk about the spine. Okay, and then here, I can go one intersection more, so this gives me something 4-dimensional, and then I'm done here. Okay. Yeah, pretty good. Yeah. Okay. So this is then, I mean, this here is really the Higgins question, it's the bisections. This is, here I'm doing 3 things, so these are trisections. Here do 4 things, so these are kind of quadrisections. And, yeah, okay, so this is the picture you get, okay? So initially when we thought about this, we thought that the best one could hope for is actually always just to hope for the spine self codimension 2, yeah? Because that might have been sort of the natural generalization, but then it actually turns out you can sort of always make it have the dimension of the number of handlebodies you intersect. Okay. So anyway, so in this board, as Jeff said, he likes to live up there, so let's leave it up there. Okay. Okay. So then maybe let me sketch the proof, because it's really similar to what we've seen in dimensions 3 and 4. So the sketch of a proof is as follows. So again, we just want to construct. So want to construct triangulation of the manifold, so that we can partition the vertices into k+1 sets with partition such that the induced simplicial map from M to the k-simplex, yeah, allows us to pull back the cubulation of the k-simplex to a multisection. Pull back the standard is either 2k if it's even, or if it's 2k minus 1 if it's odd dimensional. Yeah? So this is what we ask here. Yeah. Okay, so let me then maybe use the last 20 minutes to just talk about some other constructions and more examples before I throw some more questions at you. Okay. I guess we've seen a few examples, and we've seen this crazy way of doing things with sort of barycentric subdivisions. often there are easier ways of doing it. And so for instance, Sn, you can just think of a double of n simplex. And once you have it as a double of an n simplex, it's just very simple, right, to construct a multisection. I mean, if you think of this as a double of these two simplices, then you just pick whatever partition of the vertices of the simplex that you like. And of course, it gives you a partition of all vertices. And then you just map it to, in this case, this simplex here. Yeah, and I mean, in odd dimensions, you just pair them up whichever way you want. And in even dimensions, there's someone who sort of stays alone, but that doesn't matter, right? So, the even dimensional picture, let me just draw it in dimension 4. It's just the same. So again, I think this is a double, and then you just map it to the two simplex in the obvious way. Yeah, and so this is then what we call it a standard trisection. Yeah, so this is standard trisection of the standard sphere. And in particular, if you just focus on one simplex, it gives you a standard trisection of standard ball. Yeah, by just restrict to one simplex. Okay. And so once you have this, of course, then you can talk about connected sum of multisections. Yeah, so this means that if you take two n manifolds and they have trisections, then you look for standardly trisected balls inside these n manifolds, and then you glue those together. And that's a way of then concocting new trisections from all trisections. Yeah. So with this can do connect sum of trisections. And so in particular, you could sort of think of here stabilization, and the stabilization procedure then, if you have a manifold, you want to stabilize the trisection, what is it? You just connect sum with the standard trisection of Sn that you've stabilized once. Yeah? So that's another way now of thinking about stabilization. Okay. Similarly, I mean, another example, maybe if you want to think about RPN, yeah? So RPN also has sort of a very nice triangulation that just comes from the cross polytope, yeah? And you take sort of the triangulation of Sn just coming from so plus minus the standard unit vectors, yeah? So this is really just a generalization of the octahedron, if you wish. Let me just draw sort of a two-dimensional picture. And this is E3 minus E3, E1 minus E1, E2 minus E2. Yeah? And so this is invariant under the antipodal map, and so you can just send it down here to a triangulation of RPN. And here you can just do a labeling scheme where opposite guys are labeled the same, and you sort of, again, pair them up. Yeah? And then this gives you a way of actually constructing then a trisection of RPN where, again, you get balls as handlebodies. So then use the map just from Sn to RPN. Mhm. So this thing here is called the cross polytope. Yeah, or the generalized octahedron, or I don't know what other names there might be for it. Okay. And then another sort of nice thing that's more geometric is this kind of Dirichlet interpretation. And that comes as follows. So you give your manifold M. I mean, M comes with a triangulation, so you give M a singular Euclidean metric. Yeah, by just thinking of every simplex as the standard Euclidean simplex, and then you glue them along isometries. Yeah, so this gives it a singular Euclidean metric that sort of some people like in physics as sort of a discrete model for relativity. So it's sometimes called Regge calculus. Yeah. And then what you can do is, well, if you think about your graphs, so gamma I is a graph corresponding to the ith partition set. So graph corresponding to the ith partition set. Yeah, then what is your handle body? Well, then HI is really just like in the sort of standard Dirichlet construction, but here we're not using points, we're using connected graphs. Yeah, it's just a set of points that are closer to this graph than to the others. Yeah, so where d of x to gamma I is less or equal to dx and then gamma j, or j not equal to I. Yeah, so this gives you this kind of picture for your handle body. And similarly then for the pairwise intersections and the central submanifold. Yeah? So if you think about HI1 intersect and so forth, intersect H, I, maybe R, yeah? So this is then a set of all points in M such that the distance from X to HI1 equals and so forth equals distance from X to H R. Okay. Yeah, so you get this kind of nice picture. And then of course you wonder, well, is there maybe some way of making these multi-section manifolds totally geodesic? Yeah, maybe in some kind of symmetric space or so. So here's maybe an aim. So make the multi-section manifolds totally geodesic. Yeah. So, for example, in symmetric spaces. Yeah, and so it would be nice to have some sort of cool examples of this. I'll just give you a very basic example. So take the round metric on S5. Now think of this as a unit sphere in C3. Yeah, and so now you can take 3 circles. So choose just the obvious circles. Z goes to Z0, 0. Z goes to 0, Z0. Z goes to 0, Z. Yeah. So these 3 circles, and then you look at these Dirichlet regions relative to these circles. I guess you can already see, right? I mean, what's the central submanifold when you do this? And now do this kind of usually construction, and the and what's your handlebody, right? And your handlebody HI is all x and s5, such that well, let's even write it in coordinates. So z0, z1, z2, such that so norm of zi is less equal to norm of zj and zk, yeah. And so really, if you look at this, I mean, this is just the thickened up circle. So this is really just S1 times B4, yeah. And then
bigger.
I beg pardon.
Mothers of Z1 is bigger than the other.
No, I want these. These are the points that are closer, right? Closer to the graph than to the other ones. Yeah, HI are the points that are closest to that circle. Oh yeah. Okay. Yeah. Yeah, and so then if you look at the central submanifold, what is the central submanifold? Yeah, so they're all they're all equal. Yeah, so it's actually the flat two torus, right, that you see in there. So it is the flat two torus. Yeah, given by Z pi. Oh, let's see if we put it there. Yeah, yeah. So it's very nice when it's this flat two torus, and of course the double intersections. I mean, HI intersect HJ. Yeah. And they just look like S1 times B3 here. Yeah. Oops, S1 times B2. Yeah. And dropping down dimension. Yeah. Okay. And then this is really nothing but, I mean, if you now look at this, delete what I have here, right? And if you now think about, of course, S5, and this is just a circle bundle here. Over CP2, yeah? And for CP2, we had this nice multisection by balls, right? And all we've just done is we've just pulled here the multisection, this trisection that we had here, we just lifted up to this here, yeah? Using the circle fibration. Yeah? So this is just a lift of the thing we had here, where here we had a ball, here we had solid tori. And here we had a torus, a two torus, yeah? Yeah, and so this is really just nothing but the fallback, yeah, of the standard trisection we had here. And that works in general. I mean, so if you look at S2K plus 1, then you get exactly this kind of nice, sort of totally geodesic trisection from just pulling back the multisection that you had here. So that's maybe one construction. But it'd be nice to have some more interesting examples of this kind of behavior, yeah, where you can actually make this work. And it would also be nice to have examples where you don't have points or circles, but you have more complicated graphs. Yeah, that does not.
Excuse me,
yeah.
I'm confused. Is it a flat two torus or the three torus?
Well, flat with respect to the.
I mean, you have three parameters, right? Which are in the unit circle. As you wrote it, Z0 was the.
Oh, three torus. Yeah. Sorry.
Okay, 5.
Yeah.
Okay.
Yeah. No, it's a three torus, right? And you're pulling back this two torus to the three torus. Yeah, exactly. Mm-hmm. Yeah, thank you. Mm-hmm. Yeah, it's time to stop. I'm getting mixed up with my dimensions. Yeah? So let me just then end with sort of these problems. So here's a conjecture. Maybe let me say it as a conjecture. So there's something to shoot for. So this is sort of this is concerning the uniqueness of multisections. Yeah. So I mentioned that Reidemeister Schreier says that for 3 manifolds, any 2 Hilbert splittings have a common stabilization. And Gay and Kirby showed the same thing for 4 manifolds. And in higher dimensions, of course, you can have different PL structures. And so here's then a conjecture, so 2 multisections of M have a common stabilization if and only if the corresponding triangulations are PL equivalent. And so I said that, I mean, from a triangulation, we had a way of going from a triangulation to a multisection. Yeah? There's actually also a way back. I mean, you can go from multisections to triangulations. And that, just as with triangulations, you might not be able to get a multisection on the nose, but you have to do subdivisions, and then you can get a multisection. Similarly, if you take a multisection like the one with balls, right, you don't get a dual triangulation in general. So you might have to stabilize until you get a dual triangulation. Yeah, it's a similar process. And so yeah, this is what we think is a plausible way of thinking about what could be true. Yeah?
Is this in dimension 3? Or
yeah, so in 3, as I said, so in 3 and 4 this is true. Yeah.
okay.
In 3 because of the Reidemeister-Singer theorem, and dimension 4 because Rob and Dave prove this. Yeah. Mm-hmm. Yeah. So maybe we should say yeah. So true in dimension 3. This is Reidemeister Singer, and 4. This is Gay. Okay. And so a related problem in doing this is being able to compute what I call these kind of multisection invariants, yeah, that you get from when you can look at the set of all multisections of a manifold and then try to minimize. Yeah, I mean for Hilbert splittings we try to just minimize genus. Yeah, and in the case of trisections, what you could do is, well, here again for trisections of 4 manifolds, you can again think about genera. I mean you have the genera here of the these guys, and then you also have the genera of the pairwise intersections, yeah? And of course the genus of your surface here, which dominates everything, yeah? And you can think of this maybe as sort of just a set numbers that maybe you try to sort of keep in the right triples, but then permute, yeah, cyclically, and try to maybe with respect to lexicographical ordering, you want to minimize this over all possible trisections, yeah. And so this may be one way of distinguishing manifolds. So invariant. And of course, in higher dimensions, genus is not going to be the most useful thing, right? I mean, you need to think about other invariants of higher dimensional manifolds that you want to use. Yeah. So let me maybe just put this sort of in a weak form. So can one compute multisection invariants? Yeah. I mean, let's call them sort of multisection genus. Yeah. For, and let's not be too ambitious. Let's just say interesting families of maybe even just 4 manifolds. Okay. And the question is, can we do it sort of algorithmically or another way? And then maybe a last comment, because I just have 1 minute. So is maybe topological implications. So what I'm thinking about here is analogous, let me just say this here, analogous to Cass and Gordon. Yeah, so I guess Cass and Gordon really just made the theory of Hilbert splitting work really well by sort of realizing that you can sort of talk about certain properties of the meridian disks in the handlebodies and how they meet. Yeah. So what they realized is that if you're not in a situation where you have two meridian disks that are parallel, yeah, but you do have two that are disjoint from each other, okay, then you can actually prove that your three manifold is Haken, so contains a closed incompressible surface. Yeah? So all of a sudden, I mean, from just knowing something about Hilbert splitting and the Hilbert splitting diagram, you can tell whether or not there's an essential surface in your manifold. Yeah? And that really sort of made the theory of Hilbert splittings, which at first seems maybe quite too broad because it applies to every manifold, but this was a key notion that then made it work. And so problem is to find something similar for even trisections in four manifolds. Yeah? So we don't have any good notions on even trisection diagrams or something that will tell you something about the manifold that you wouldn't know in easy ways otherwise. Okay, anyway, I'm done.
Questions?
Do you have some insight on different clear structures on the same manifold that they have, like multisection of the same manifold with different clear structure and how they can come?
Yeah, not yet. This is actually something I'm thinking about. Yeah, and that's so not in dimension 5, actually in dimension 7, because there's this is maybe a little bit easier because there's this sort of there's this fancy 7-sphere, exotic 7-sphere that has a lot of symmetry. Yeah, and so that's maybe a good first example to try to see whether in this way you can actually really distinguish the smooth structure on this or the PL structure on this from the standard PL structure. Yeah. Mm-hmm. But this is all work in progress. Uh-huh. Yeah.
Any further comments?
So about your realization problem, can you solve this for some 6 and for k equals 3 for if I give you a hyperbolic symmetry?
Or even k equal 2. I mean, you give me a surface with any. So the way I really wanted, is you give me a cubulate. I mean, you can get all surfaces, but I really want the cubical structure to see in the class. Yeah, it seems very hard. So even if you just give me any,
Okay, I was just thinking of
the underlying, yeah, and that of course you can get all surfaces. I don't know whether I can. I mean, I haven't tried yet to get all hyperbolic 3 manifolds.
But an opposite curve
Mm-hmm.
cubing gives you a restriction that topology,
Yeah.
Any cubing.
No, I mean any. Of course, I mean any non-positively curved cubing.
Yeah, positive curve.
But I didn't want to. I mean, in the strong version, I do not want to change the cubing. I then want to keep the cubing and then build a manifold. So then you already know, right? When you have one top-dimensional simplex for each cube, and you're sort of supposed to put them together in the right way. Yeah.
Great, then let's thank the speaker for his wonderful lecture.